In yesterday's lecture, we talked about how we can use what we refer to as an analysis of variance to check to see if at least one of the means of several different populations is different from the means of the others. So today we're going to talk about a two-factor ANOVA, and you can actually extend this idea to multiple factors. So here's the idea behind this. So we have, say, a population that we can split into different pieces. So maybe, for example, we could split our U.S. population into, say, two factors, male and female, and maybe split it into geographic regions. Okay, we wouldn't expect, for this particular example, what we're going to assume is there's not any interaction between the factors. We'll talk about interaction actually when we do the lecture. But right now we're going to assume that there's no interaction between rows and columns. So, for example, if I split gender and geographic region, there's no reason to expect that there's going to be some interaction between, say, being female and being from the Midwest versus being female and being from California, for whatever purpose that might serve for our study. Say that there's probably not interaction there. However, if you split your population into gender and, say, height, then you would expect that there would be some interaction between those particular factors because, on average, men are taller than women. So anyway, we'll talk about interaction when we actually do this in class. But for right now, we're going to assume that there's no interaction. So for that purpose, we're going to assume that there's only one observation in each of these cells in my table. So let's assume that we've got our population split into A, row factors, and B, column factors. There's only one observation per cell, assuming that there's not any interaction. So, for example, maybe you do the means of what you have and put them in each of your cells. So you only have one observation. That certainly would be something that could be considered normally distributed. And as long as all the variances are equal, we could assume that as long as you have the same sample sizes, you could assume that you had the same variance as well. So anyway, for the time being, we're going to assume there's only one observation per cell and that there's no interaction. And then each of them is normally distributed. We're going to assume that common variance idea. And then each of these observations, each of these cells have their own means. All right. If the various factors have no effect at all, meaning there's nothing different in this observation versus this observation versus this observation and so on down the line, then each of these means should be equal to an overall mean of all of these taken together, which should be mu. There shouldn't be any difference in those things. All right. However, if they do have an effect, then what we're going to assume is that the individual means depend not only on the overall mean, but also what row and what column we're in. So we're going to assume that this happens in some sort of an additive way. So this mu is representing our overall mean. The alpha sub I is representing the effect of being in row factor I, and the beta sub j is representing the overall effect of being in column factor j. Okay, so we're going to assume this happens in some additive way. We could assume that overall, if we sum up all of the row effects and sum up, that should be 0. And if we sum up all of the column effects, that should be 0. You should look at the book on page 390 for an explanation of why we can make this assumption. Basically, it's just you're shifting the effects to make sure that we actually sum up to be 0. That's all it really is. It's not that big of a deal, but if you're really, really interested in why we can make that assumption, they have the explanation. It's a short explanation near the bottom of page 390. Let's see what I'm talking about with a specific example. This is problem 7.6-2 in your book. Let's say we have 3 row factors and 4 column factors. This one asks you to find the overall mean, each row effect, and each column effect if the individual means of the cells are given by that table. All right. Well, the overall mean piece is pretty easy to find because to find the overall mean, if these really are adding up to 0, to find the overall mean, I just need to figure out the mean of all of the individual means. So we can do that in this case, and we get 8, just adding them up and dividing by 12. Again, the reason why we can do that is because these the assumption that we're making here is that these overall row and column means are column effects are 0. All right, so to figure out each of the effects, we just take the means on each row or column, depending on which effect we're looking for. So if we go across row 1 and take the mean, I get 6. Right? So the effect of being in row 1 is that it's 2 less on average than the overall mean. So the row effect of row 1 is -2. Doing a similar thing for row 2, taking the average in row 2, we get 10. So on average, being in row 2 means you're 2 above the overall mean, so that row effect is 2. And then if you take the mean of row 3, you get 8. Being in that row is has the same effect, essentially, as being overall, so the row effect is 0. And then you do the same thing for the columns. Just in this case, we have 3 items in each column instead of 4, and you can check that those means are 8, 5, 9, and 10. And again, just as a quick explanation for column 5 here, or excuse me, column 2 here, the mean is 5. Overall, the mean's 8, so being in column 2 would make you have a mean of 5 overall if you spread it out over the whole column, so that column effect is -3. It's 3 less than the overall mean. All right. So as another example here, just to show the additive nature of our model, if we look at the mean sub 2,3, mu sub 2,3, that's 11. Notice the overall mean is 8, so that's our mu piece. The row effect of being in row 2 would be adding 2 to that 8, so we get 10, and then the overall effect of being in column 3, it's not the overall effect, the effect of being in column 3 is having adding a 1 to the mean, so we would have a +1 there. So that's just breaking up into its pieces. All right, so what are we interested in here? Well, the idea is we want to know if being in a different factor actually matters. Okay, so just some examples here. If you are testing, say, a particular medicine, maybe you want to know what's the effect of you have different effects, different medications that you're given based on for a row effect, and then maybe you're basing it on maybe age factors of the population, or you're basing it on gender, or you're basing it on pregnant or not. There are all sorts of ways that you could break it up into factors of testing your medication and what effect it has on a particular segment of the population. So you'd have different medications in different segments of the population. So you've got those 2 factors that are going on. And again, you can see how this could be, you've got maybe 3 factors and wanted to know if comparing those 3 factors and then perhaps how they interact. That's, like I said, we'll talk about interaction when we talk about this in class. But anyway, our hypothesis test is going to be here in 2 parts. So what the first hypothesis, our H sub A, is going to be is that there is no row effect, meaning it doesn't matter what row you're in, you should have the same mean as you do overall. And then similarly for the H sub B here, that is also that there is no column effect, meaning that each of the column effects are 0, so it doesn't matter what column you're in, it has no effect on your mean. It's the same as the overall mean. All right, so how are we going to test this? Well, it's going to look a lot like what we did in the previous section, what we talked about yesterday. So we have an overall total sum of squares here. So we do each observation minus the overall mean squared, just like we did before. And we're going to break it into pieces. We're going to break it into a row piece, a column piece, and an overall piece, if you will. Now, I'm not going to go through all of the algebra, but this can be rewritten in the following form, where you have a B times that sum from 1 to A of that piece along your rows, an A times the sum along your columns, and then this double sum here. So we're going to call those 3 different pieces here. You're going to have the first one's going to be SSA. So it's the sum of squares for your factor A. You have an SSB, your sum of squares for factor B, and then you're going to have an error sum of squares, again, like we had before. So you should go back and compare these two sums back to the previous section, section 7.5, because it's the same idea that we did there. If you look at what we talked about in class, and if you look at the expression that's on page 381, each of these should look like SST, right? This looks like a treatment sum of squares, a between treatment sum of squares along your rows. This is a between treatment sum of squares along your columns. In that case, we had an n sub I in here. Well, notice that the a and the b don't depend on the I or the j, so you could just pop them out in front. So these literally are the same types of expressions that we had for SST in the previous section. All right, so let's talk about the distribution of these pieces. Well, first, notice that this last piece, assuming the additive model is correct, this last piece, SSE, doesn't depend on mu sub ij at all. Okay? What I mean is that if you look at, there's a little bit more to it, but if you look at it, notice that the x sub ij minus x bar sub I and minus x bar sub j, notice that it looks like mu sub ij minus alpha I minus beta j. And if we assume that our additive model is correct, that's just moving alpha sub I and beta sub j over to the left-hand side and leaving mu on the right-hand side. So there isn't a mu sub ij, it's just a mu that's over here. Okay. So what this is really just a computation of an individual observation and the mu sub I, the mu piece. So again, notice that there really isn't a mu sub ij in there at all. So what that means for us is no matter whether or not these null hypotheses, we have two null hypotheses we're talking about. We're doing two hypothesis tests essentially at once. Assuming that these, no matter whether or not they're true, that SSE is going to have the exact same distribution. Okay, so we can use it, like your book says, you can use it as a measuring stick. Now I'm just putting this up here for reference for the different pieces, all right? So we look at this, we have it broken into several pieces. I already said that this is our total sum of squares. We already talked about this, it's the same total sum of squares we had in the last section. So we already know that this, if I divide it by the variance, I get a chi-squared distribution. These two look like your between treatment sum of squares, and we also know that those, if we divide by the variance, gives you a chi-squared distribution. So, looking at your degrees of freedom, there are A, B total observations over here. So this is going to be, these should be divided by sigma squared, by the way. This is not SSTO. It should be SSTO divided by sigma squared. That's chi-squared of AB minus 1. Same thing here. This should be divided by sigma squared. This piece here, like we talked about with the between treatment sum of squares, this is going to be chi-squared of A minus 1. Because there's going to be A minus 1 pieces here. And then likewise, if I divide this by sigma squared, this should be chi-squared of B minus 1. So again, like I mentioned before, compare that to what we did back in section 7.5. Well, and we talked about this as well. If this is chi-squared, and this is chi-squared, and this is chi-squared, and everything here is independent, then that final piece should also be chi-squared, filling in the missing degrees of freedom. And you can check that if I take A minus 1 plus B minus 1 plus A minus 1 times B minus 1, you really do get AB minus 1. So this last piece really is also a chi-squared of A minus 1 and B minus 1, and this is the piece that we know doesn't change no matter whether or not there's a row effect or a column effect. So if our null hypothesis is true for the A's, then both of these are independent chi-squared random variables, so that if I divide out by the degrees of freedom and move the sigma squared out, we get unbiased estimators of sigma squared. So if we do the ratio of those two pieces, if they really are independent and there is no row effect, if HA is true, the ratio here should be close to 1. However, if the HA is not true, then just like what we talked about in the previous section with our treatment sum of squares, this gets bigger. The expected value gets bigger. So if I do the ratio, that ratio of SSA to SSE, and then of course dividing out by its degrees of freedom, that ratio should be getting bigger than 1. So we'll use an F distribution and reject if that ratio gets too large, depending on how many degrees of freedom we have and what significance level that we want. Now, of course, we're not going to do all of this by hand. We'll use Excel for all of these computations. which is what I'm going to focus on doing in class rather than going through all this explanation in class and wasting the class time and the internet bandwidth on this. So anyway, I know there was a lot of talking in this particular one, but I really want you to focus on this expression at the top of why things are true here. We've got chi squared, chi squared, chi squared, so this had to be chi squared. This one's distribution does not change no matter what happens. It's these two that can change depending on if we have a row effect or a column effect. Okay, so that's why we use the F distribution to help us determine whether or not there is a row effect or column effect. Now, I only talked about this for H sub A, but you would do the exact same computation for H sub B. If there is no column effect, this also should be, if I take SSB and divide it by B minus 1, I should get an unbiased estimator for sigma squared. If HB is not true, then I get something that should be, on average, bigger than sigma squared, and so that ratio would get bigger. So we would still use an F test to do it. So again, like I mentioned, we'll do Excel for all of this stuff. I just wanted to tell you where this stuff is coming from, why we're doing an F test, what that F statistic means in Excel when we do this, because all we're going to do in Excel is use a data analysis package, and it's going to spit out some values, and we're going to grab those values. But it really is important to understand what those values are telling you and where those values come from. So that's why I wanted to make sure I went through this particular video. So anyway, we'll talk more about this in class tomorrow.